Hello and welcome to a video about empirical formulae, formulae being the plural for formula. This is for the higher tier for GCSE chemistry, but probably useful for any qualification that you might be doing. We're going to be looking at how to work out the empirical formula of a compound from either the masses or the percentages of the elements in that compound. The first thing we probably need to look at though is what we mean by empirical formula. So written it out over here for you. The empirical formula is the simplest whole number ratio of atoms of each element in a compound. So we look at the ratio of the atoms of each of the three different or two or however many different elements, and we compare those ratios, and that helps us to work out the empirical formula. Now just to give you a bit more explanation on that one, have a look at this. We've got ethene, which has a formula of C2H4, but the empirical formula is the simplest ratio of atoms of each element, and the simplest ratio would be C1H2. So if we divide both of those by 2, we'll end up with C1H2, and there I've written it down there for you. Okay, so that's the empirical formula. This in fact over here is called the molecular formula, because it actually tells you the actual number of atoms of each element. But this one, in its simplest form, the ratio of the two atoms gives you the empirical formula. Now we can have a look at one more just to make sure we completely understand this. Another example is a substance called propene. Its molecular formula is C3H6, but the empirical formula is also the same, it's CH2. So if we simplify the number of, or the ratio of atoms of carbon and hydrogen, we have 3 to 6, that can simplify to 1 to 2, so then we write it out as C1H2. We don't write the 1, so it's CH2 as well. Okay, so next stage is how do we actually work these out from information given. So let's have a go at that. Now the first thing we need to be able to do really is to work out the ratio of the amounts of the atoms in a compound of all the different elements. So if we can work out the ratio of the amounts of atoms, we can then work out an empirical formula. Now if you've looked at a previous video I've done on this about moles, we can actually work with this quantity called moles, because that's what we often work with in chemistry, and if we can work out the ratio of moles, we can again work out that empirical formula. So let me give you a simple example to have a go at. Here we have a question that says a compound contains 1 mole of carbon, 2 moles of hydrogen and 1 mole of oxygen. What is the empirical formula? Well, if we're comparing moles, they're actually done here for you. So we've got carbon, we have 1 mole, I could put a little 1 there. Hydrogen, we have 2 moles, and oxygen, we have 1. So we can actually write this out as CH2O. We don't write out the 1s there. So that's the empirical formula for this substance here. All we've done is we've looked at the moles of each of our elements and written it in the simplest ratio, 1 to 2 to 1, and there's the answer. Now unfortunately it's not always that simple in an exam. You do have to be able to do what it says here, calculate the empirical formula from masses or percentages. Right, so we're going to have a go at working out the empirical formula from some masses of this compound. So I've broken it up into this kind of framework to make it a bit easier to work with. First stage would be to look at our 3 different elements, or however many different elements you have. Here we have carbon, hydrogen and oxygen, and we're going to put them in columns just to make it nice and simple. Now the first step is to divide the mass by the relative atomic mass for each one of our elements. Okay, so we've done a video on relative atomic mass and so on. These numbers have been given here for us to work with. So divide each mass by the relative atomic mass for each. So for carbon, what we do is we have a mass of 2.4 grams, and we divide it by the relative atomic mass. That will give us divided by 12, which is here, and that will give us an answer of 0.2. For hydrogen we have 0.4 grams. The relative atomic mass for hydrogen is 1, so that's divided by 1, so we have an answer of 0.4 4, and for the last one, oxygen, 3.2 divided by 16. Again, that gives us 0.2. And what we've actually done here is we've actually worked out the number of moles of each of these substances in this bit of information that we've got here. The number of moles is actually found by dividing the mass by the relative atomic mass. This is not a requirement that you know that formula for the specification, but just for your information, that's what we're doing. We're working out the number of moles of each. Now for the next stage, we want to work out a nice neat ratio rather than 0.2 to 0.4 to 0.2. We want a nice neat ratio, so I've said simplify the ratio, divide each by the smallest. Now it's fairly obvious for this one, but let's just do it so that we know. 0.2, we divide it by the smallest number, and the smallest number is actually 0.2. So 0.2 divided by 0.2 is 1. 0.4, again, divide by 0.2, that gives us 2. And for oxygen, 0.2 divided by 0.2 equals 1. So there we have our nice simple ratio to work with, and the final stage then in this is writing the formula. So very simply, we've got carbon 1, hydrogen 2, oxygen 1, and because it's 1 here we don't need to write it out, so the empirical formula is CH2O. Now this is actually the same example as we did here. Here I gave you the moles, but for this example we've found out how we actually got to that ratio of moles from some data. Okay, so that's the steps for working this out. If you're quite happy, you can pause here and have a go at this one. However, there's a little tricky bit with percentages. If you're not happy, keep going, and we'll go through this answer, and then I'll give you one to do by yourself from a past paper at the end. Okay, so again, we're calculating the empirical formula, but this time we've got percentages and not masses. Okay, and this is very easily dealt with, because all you can do, or all you have to do, is just get rid of the percent and put a grams in there instead. So just convert all those directly to grams. It actually works out as the same thing. You've got the same proportion of each element in there. Okay, so we've done that stage there, and then we just do what we did previously. So to work out the empirical formula, stage 1, divide the mass by the relative atomic mass for each. So we've got a mass of 18.2 for potassium, 18.2, and we need that number there, which is 39. So divide by 39, and the answer is 0.47. We do a similar thing for iodine. We've got 59.4, divide that by 127, and fortunately and nice and neatly for us, it's 0.47. And for the last one, for the oxygen, we have 22.4 divided by 16, and the answer there is 1.4. Next stage was to simplify the ratio, so divide each by the smallest. So these are the numbers we'll be working with, and we divide through by the smallest. So for potassium, 0.47 divided by 0.47. For iodine, which is next, it's again 0.47 divided by 0.47, nice and simple. And for the oxygen, it's 1.4 divided by, again, 0.47. The answers are as follows. This is 1, this is 1, this is actually 2.97. Now this happens sometimes. We don't often get exact numbers, because there could be, when we were working this out in our experiment, there could be some experimental errors or some inaccuracies. You might have lost part of one of these compounds or something, and you might not get an exact number, but we can see here that 2.97 is pretty close enough for us to call it 3. So our formula works out like this. So next stage is to write the formula. So it would be KIO, and it's 113. We don't need the ones there, so it just becomes KIO3. This is actually, I believe, potassium iodate, but that's not the key thing. That's not the important thing. The important thing is we're able to work out the empirical formula, and if you follow these steps, you should be able to work it out. Now for the final part then, Hopefully you're feeling a little bit more confident. What I want you to do is to work out the empirical formula based on the data here. This actually comes from a past paper question, and it was worth 4 very valuable marks. So if you were given a question like this for 4 marks, how well would you do? Why don't you give it a go, pause here, give it a go, see how you get on, and then I'll give you the answer when you're ready. Okay, so I haven't written out all the different steps here. You can refer back if you want to, but I'm going to go through it step by step, see how you did. Right, so the first thing is, remember, we divide each mass by the relative atomic mass. We've got percentages here, so I can just very simply change that to grams, and then I can divide these grams by the relative atomic masses. So let's do our columns first. We've got iron, which is Fe, and let's have lots of space, and over here we'll do our oxygen, which is O. So first step, 70 divided by 56, 70 from here and the 56 from here, and that gives me an answer of 1.25, and remember this is working out the number of moles. And for the oxygen, it's 30 divided by 16, gives me an answer of 1.875, and so these are the number of moles of each, but you can see it's not as easy to simplify as it was for one of the previous questions. So we then, next stage is divide through by the smallest. So we take these numbers, divide through by smallest. We have 1.25 divided by 1.25, and then for oxygen we have 1.875 divided by 1.25. Quickly work this out. That's very simply 1. This over here is 1.5. Okay, so we've got a 1.5. That's not a whole number. You'll remember previously that we said it's got to be the simplest whole number ratio. You can't have half numbers. So the way we can deal with this is not down to experimental error, it's actually right in the middle of the two. So what we can say is we can double this and double this. We do the same to both. We end up with 2 for that and 3 for that. So this is the simplest whole number ratio, and then you end up with a formula that goes like this: Fe2O3. So this is the empirical formula for iron oxide based on the data given. This was worth 4 marks in an exam, as we said, and if you got through these steps that we've done here, 1, 2, 3, 4 marks for this question. So hopefully you're feeling a little bit better about empirical formulae and you feel like you're able to do some of these questions. If not, maybe go back and have a look again. It's relatively straightforward, just takes a bit of practice.